AWS Identity and Access Management functions as a high-speed cryptographic evaluation engine. It intercepts and interrogates every API request attempting to enter your cloud infrastructure. Modern cloud architectures execute thousands of these API requests every second, driven by constant communication between microservices, databases, and developers. To understand why this engine is so critical, you have to look at the AWS shared responsibility model. This is the foundational law of cloud security. AWS controls the bottom half of this model. They are responsible for securing the physical data centers, the hypervisors, and the raw compute hardware running your instances. You control the top half. You are solely responsible for securing your data and the API access layer that sits in front of it. In that top half, IAM is your primary defense mechanism. It is the boundary line between a secure architecture and an open vault. If you misconfigure IAM, the biometric locks and armed guards at the AWS physical data centers mean nothing. A single logical routing error in your access policies will compromise your entire infrastructure. Before we write the rules, we must classify the actors. Who or what is making requests? In this access taxonomy, a principal is any user or workload making a request. Moving inward, an entity is authenticated, while an identity is authorized. At their intersection sits the IAM user with long-term credentials, alongside the credentialless IAM role. Instead of being permanently assigned, roles are assumable. They provide temporary, dynamic access to anyone or any machine that requires it. Meanwhile, the IAM group sits outside the authentication circle. It cannot make requests. Finally, the AWS account root user sits uniquely outside these boundaries, possessing ultimate, unrestricted authority. With actors defined, we introduce the rules. IAM policies are strict JSON documents attached to these identities, dictating exactly what they can and cannot do. This diagram shows AWS managed policies. These are standardized, pre-built JSON documents maintained by AWS, and they can be attached across multiple accounts. But broad access is dangerous. In production, you write custom managed policies. As you can see here, these are custom-tailored documents explicitly mapped to specific roles and groups. Let's trace how policies evaluate an API call. A principal submits a request containing their intended action, target resource, and session context. The request hits authentication first, verifying the provided keys, before entering the critical authorization policy evaluation phase. The engine operates on a foundational rule. The default state of every single request is an implicit deny. By default, no one has access. To grant access, you must write an explicit allow inside a policy. This overrides the implicit deny and permits the action. The logic gate prioritizes one instruction above all, the explicit deny. If the engine finds a single explicit deny, evaluation stops instantly and the request is killed. Only by passing this strict authorization gate is the action finally passed to the AWS service. The engine processes this logic ruthlessly. Failing to understand how an explicit deny overrides an explicit allow is the leading cause of catastrophic access bugs. Beginners often start by generating long-term static access keys for their users and embedding them in code or local workstations. This creates an immediate vulnerability. Static keys rot. Accidentally committed to public repositories, they provide a permanent, compromised access vector into your infrastructure. The solution is to remove static keys entirely using the AWS Security Token Service, or STS. STS dynamically generates short-lived credentials, and Identity sends an assume role API call to STS. STS verifies the request, returning a temporary access key, secret key, and session token bound to a strict countdown timer. By assuming this role, the identity temporarily morphs, adopting its limited permissions. When the timer runs out, the credentials automatically expire. There's no need to manually rotate keys, and a leaked session token becomes completely useless. Moving from static users to STS-driven roles aligns your architecture with the standard for professional cloud security. We can apply this STS theory directly to workload communication. Consider an EC2 instance that needs to read data from a secure S3 bucket. In this architecture diagram, we use an instance profile. This mechanism attaches an IAM role directly to the EC2 instance. The instance automatically pulls temporary session tokens from the metadata service, using them to access the bucket. Because of the instance profile, the application code requires 0 hard-coded keys. The infrastructure handles the cryptography natively. This same STS logic applies to human access across organizational boundaries. In this cross-account topology, a developer in a centralized identity account needs to deploy code into an isolated production account. The production account uses a trust policy as a strict gatekeeper, verifying it explicitly trusts the identity account before allowing role assumption. True zero-trust architecture relies entirely on this mechanism, enforcing temporary role assumption across all human boundaries and machine interfaces. This JSON block shows the wildcard trap. It is an incredibly dangerous engineering practice, where an asterisk is used for actions or resources in a policy. Using wildcards violates the mandate of least privilege. It grants broad, sweeping access that opens massive attack vectors, allowing compromised identities to move laterally through your environment. You must also account for the account root user. Because it inherently bypasses standard IAM constraints, its credentials must be locked away, and its sign-in secured with strict multi-factor authentication. To actually enforce and maintain least privilege at scale, you need an auditing mechanism. That mechanism is AWS CloudTrail. CloudTrail captures the exact identity and policy used for every API call. By analyzing this data, engineers can reverse engineer perfect, highly restricted least privilege policies. Effective IAM requires continuous auditing and refinement. Your security posture relies on treating access control as an active, evolving layer of your infrastructure.